Hi guys, this is lesson 3, exercise 90, planar graphs and Euler's formula. Now, ideally, these videos are for the students that were on the Queensland camp. But if you want to watch these videos as a refresher, you are more than welcome to. Hopefully this will be posted on YouTube, or alternatively on Compass. So, before we get into the different types of graphs and planar graphs and Euler's formula, I will say that it can get, from now until onwards, it can get a bit daunting having to see all the different terminologies and different establishments that you can have on graphs. Just make sure that you read your notes thoroughly and have them there as a handy reference, because it can get confusing having to establish the difference between all of them. And you'll see later on how it can get confusing. Okay, the work is relatively easy. Just establishing the differences can get kind of tricky. Anyways, a planar graph, it can be drawn on a plane. So we're looking at a graph that can be drawn on a plane, flat surface, so that no edges will intersect or cross each other, except obviously at the vertices. So right here, this is an example of a planar graph. All the vertices are separated and there's no intersections between the lines or the edges. So some graphs do not initially appear to be planar. So if you look at this example here, graph 1, this is a non-planar graph. Okay, the reason why this is non-planar is because the edge from A to D and the edge from C to E, they have an intersection right here. But you can draw this to make it equivalent and then also make the graph actually planar in itself. Okay, so when a graph is equivalent, it's isomorphic. And this graph here, graph 1 and graph 2, are exactly the same graph. The only difference is graph 2 is to be considered as a planar graph because there's no intersections. So what's exactly happened is, if you can imagine these as pins on a board, and these are strings that connect these pins, all I've done is taken pin D, still having the strings connected to it, and then moved it into the middle here to replicate this. Obviously, the connection from C to E is a straight line here, but C to E is curved. It makes no difference whatsoever. The connections from each vertices are still the same, but there's no intersection. So this is non-planar, and this is planar. Now, not all graphs are planar. So if we take this example here, the graph here to the left, it cannot be redrawn in an equivalent planar form no matter how hard you try. So this example here is pretty obvious, but these examples here, you can't redraw this in a planar form. Now there's no set formula or specific process to get from a non-planar graph to a planar graph to see if it is planar. You just have to use trial and error and use your imagination to try to figure this one out. You can go ahead and see if there's a way to make these make this graph planar. There's no way. Okay, so we'll look at this example here. Example 1, show that the following graph is planar by redrawing the graph so that no edges intersect. Now there are different ways that you can do this. A really simple way for this graph to make it planar is, again, pretend that all of these vertices are pins and all the edges are strings. Take the pin out, this pin R, and plunk it into the middle here so it becomes planar. Okay, really simple. So go ahead and copy this one out. Just make sure that you still label your vertices when you're copying that. Okay, so this planar identity will be then used to determine how we establish faces of a graph. So a graph, this one here opposite, can be regarded as dividing the paper it is drawn on into two different regions. Now you can have more regions depending on how this graph is drawn, but in this specific graph, we have faces. Okay, one face is F1 is bounded by the graph, or in other words, it's inside the specific graph that we've drawn. Okay, so this is F1. The other face, F2, is a region surrounding the graph. It's almost like the outside face, and this outside face technically is infinite. It keeps going on forever and ever and ever. Okay. So we would say that the number of faces for this specific graph is 2, inside and the outside. And we'll look at this example here. For each graph, identify the number of vertices, edges, and faces. So vertices being the points, edges being the lines, and the faces being bound and on the outside. So number of vertices in this case, 1, 2, 3, 4, 5. So say b is equal to 5. The number of edges, 1, 2, 3, 4, 5, 6, 7. So there are 7 edges, and the number of faces, 1, 2, 3, which is bounded inside of the graph, and then the external, the outside face, is the 4th one. So in this case, there are 4 faces. Now, example B, it's easy to get the number of vertices and the number of edges. So it's 4 apiece. You've got to be careful though with the number of faces. If you look at this non-planar graph, you could say that there are 1, 2, 3 faces, 2 on the inside and 1 on the outside. However, this is non-planar. We have to make, if it's possible, we have to make the graph planar. Or in other words, we can't have an intersection. So we're going to rejig this, change this around so that A and F are swapped places. And by doing so, we've almost like untangled the graph, so it becomes planar. So now that we've done that, they're still isomorphic, they're still the same graph. It's just one's non-planar, the other one's planar. We can then determine how many faces that this graph has. In this case, 2 on the inside and the external one. So F is equal to 2. Now that we've established planar graphs and how we can count vertices, edges, and faces, we're going to use this information with Euler's formula. Now, Euler discovered that, and there's a big proof behind it, and it takes forever to read, and it's really, really complicated. But anyways, Euler discovered that for any connected planar graphs, so connected meaning that every single vertice has to be connected one way to another vertice, and it has to be planar, so there's no intersections. There is a relationship between the number of vertices, the number of edges, and the number of faces. And this relationship can be expressed as you take the number of vertices, count that, you subtract the number of edges, count that and subtract it away, and you add the number of faces, you will always get 2. Your answer will always be 2. The actual formula itself, V minus E plus F is equal to 2. So I can draw any graph with any amount of vertices, provided that they're all connected, and provided that there are no intersections, or they're planar. If I count each of these vertices, edges, and faces, and plug it into this formula, I will always get the number 2. And you can look at this specific example here. The number of vertices is 6. 1, 2, 3, 4, 5, 6. Number of edges, 8. 1, 2, 3, 4, 5, 6, 7, and 8. number of faces for 1, 2, 3 interior, and then 4 for the exterior. Plug it into the formula, 6 minus 8 plus 4, vertices, edges, and faces, and the formula is verified. It's equal to 2. You can attempt or create any type of graph, provided it's planar, and provided that it's connected. You will always, when you figure out these numbers, will always get 2. And this section here, there will be some questions where you can transpose this formula, v minus e plus f equals 2, and by doing so, you can find either how many edges a certain graph might have, how many vertices a certain graph might have, or how many faces a certain graph might have using this formula. It's just being rearranged. So give me the number of edges, how to find the edges, vertices, and faces is what you need to get the vertices, edges, and faces. And last one for the faces, get your edges and your vertices and just plug them in. Alright, these different examples, I might scroll out just a bit so we can put that all in there. Yep, there we go. So a connected planar graph has 10 vertices and 6 faces. Determine the number of edges for this graph. But to get the edges, I use this formula. Plug those numbers in. So vertices 10, faces 6, and then subtract 2. You end up getting 14. So if I had a specific graph, and I put 10 vertices, and I knew it had 6 faces, the amount of edges has to be 14. There's no other number that could work. Okay. Same thing here, connected planar graph has 4 vertices and 6 edges. Determine the number of faces. We just use this formula here. So 6 minus 4, edges and vertices, plus 2 is equal to 4. So we're expecting 4 faces with 4 vertices and 6 edges. And the last one, connected planar graph has 8 edges, 5 faces. We're trying to determine the vertices or the amount of vertices. Plug in edges, plug in faces, and work this out to the amount of points for vertices. For this case, is equal to 5. And that concludes this lesson, lesson 3 of exercise 9D. Go ahead, check your logbook, see what questions you need to complete for this set exercise. Catch you in the next video.